modern cosmology operates under a dominant paradigm known as the heliocentric globe model, which describes Earth as a spinning spheroid orbiting the Sun within a vacuum environment governed by gravitational forces. Despite institutional consolidation, this paradigm is seldom subjected to first principles falsification using physical evidence available to non-institutional observers. Instead, validation is usually delegated to professional expertise, institutional authorities, classified or inaccessible domains, non-reproducible demonstrations, or consensus as a stand-in for evidence. This raises a rarely considered epistemic problem, namely, is the globe model empirically verified, or is it institutionally maintained? A model qualifies as scientific only to the extent that it is testable, meaning claims can be evaluated against physical reality; falsifiable, meaning model failure is logically possible; reproducible, meaning experiments yield consistent results; and independent of authority, meaning truth is not contingent on institutional validation. For a cosmological framework, these criteria must apply at the level of physics, geometry, environmental behavior, and observational confirmation. If a model fails these criteria, it is not necessarily false, but it ceases to operate scientifically and enters the domain of belief, consensus, or institutional narrative. In modern society, many claims are held not through direct verification, but through trust chains. For example, Earth curves, Earth spins, gravity holds the atmosphere, space is a vacuum, objects orbit Earth, the Sun is 93 million miles away, and water curves around the Earth. For the average person, and even for the average scientist outside of specific fields, these claims are not observed directly and are instead validated by things like textbooks, images, the education system, the mainstream media, institutional statements, and consensus. These may constitute a trusted knowledge domain, but not a scientifically verified one. In contrast, claims like water seeking level, gas pressure equalizing, vacuums requiring containment, and objects visible at long distances are directly verifiable without institutional mediation. These are empirical domains that do not require trust chains. The burden of proof lies not with the challenger, but with any model making claims that contradict direct sensory evidence, physical laws, laboratory demonstration, or experimental reproducibility. Two examples clearly illustrate this principle. If a model claims standing water curves, the burden lies on the model to demonstrate curvature in a natural or controlled setting. If a model claims gas pressure can exist adjacent to a vacuum without containment, the burden lies on the model to demonstrate such a system. Appealing to theoretical constructs, like saying gravity does it, without a reproducible demonstration, fails the burden of proof. Authorities can be wrong, and have been historically, across many domains, including physics, astronomy, and cosmology. Thus, institutional consensus can only be treated as a claim and not proof. Certain phenomena sit at the top of the credibility hierarchy because they are directly observable, repeatable, and instrument confirmable. For example, the phenomenon of water seeking level is an empirical, repeatable, and directly observable claim that anyone can confirm for themselves. The phenomenon of vacuums requiring containment is empirical, repeatable, and experimentally verifiable. And the phenomenon of the horizon revealing more with magnification is also empirical, repeatable, and instrument confirmable. In contrast, the phenomenon of Earth curvature is model-dependent, indirect, and theoretical. The phenomena of stellar, solar, and lunar distances are derived, indirect, and theoretical. And the phenomenon of outer space being a vacuum is institutional and inaccessible. In the hierarchy of credibility, direct empirical phenomena hold greater weight than indirect institutional claims. This doesn't completely invalidate indirect claims, but it does prevent them from serving as defeaters against direct physical behavior. Once these epistemic rules are set, the evaluation becomes straightforward. A cosmological model must be able to demonstrate its claims physically, explain observed behavior without contradiction, operate without unverifiable escape clauses, and withstand falsification attempts. If it fails in any domain, scientific rigor demands revision, reduction, or replacement of the model. This is not controversy or conspiracy, it's the scientific process. So let's now examine the three scientific test vectors mentioned earlier, namely hydrostatic equilibrium, or water-seeking level, thermodynamic containment, Kelvin's second law, and optical occlusion, the fact that we see too far, and assess whether these core physical phenomena align with the heliocentric rotating spheroid model or an enclosed stationary plane framework. In all experimental and environmental contexts accessible to human observation, water exhibits the following behaviors. It assumes the shape of its container. It equalizes via pressure. It settles into hydrostatic equilibrium, and it forms a planar horizontal surface. This behavior is consistent across all scale domains, from the laboratory, like beakers, graduated cylinders, and basins, to engineered, like reservoirs, canals, locks, and ballast tanks, to natural, like lakes, bays, seas, and oceans. In no domain does standing water spontaneously curve across its surface. The globe model, however, asserts that oceans conform to the curvature of a sphere 3,959 miles in radius. The standard curvature approximation used for a globe of these proportions is a drop rate of 8 inches times the mile squared, meaning at 10 miles there would be 66.6 feet of predicted drop. At 50 miles there would be 1,666 feet of drop, and at 100 miles there would be 6,666 feet, or well over a mile, of curvature drop. Under hydrostatics, water level is defined as flat, and curvature is not observed as a first-order fluid phenomenon. Under the globe model, however, water level is claimed to conform to curvature at a planetary scale, but still remains flat locally. This introduces a discontinuity between local physical law and a global geometric requirement. Crucially, no laboratory experiment demonstrates hydrostatic curvature as a function of scale. This claimed behavior exists only at planetary scale, beyond empirical demonstration. Thus, absent demonstrational evidence, spherical water curvature remains model-dependent, scale-dependent, and unverified empirically. This alone may not falsify the globe model, but it does shift the burden of proof to those asserting such non-local fluid behavior. Next, let's examine gas pressure and thermodynamic containment. Gas pressure arises from molecular collisions against container boundaries. Under the second law of thermodynamics, gas expands towards regions of lower pressure until equilibrium is achieved. This behavior underlies things like pneumatics, engines, pressurized cabins, scuba systems, and industrial vacuum chambers. Now, the heliocentric globe model asserts Earth's atmosphere is a high-pressure gas, 14.7 psi at sea level. Space is a near-zero pressure vacuum. No solid barrier or membrane exists between them, and the interface is maintained solely by gravity. This would make Earth the only known system where high-pressure gas is held adjacent to a vacuum without a barrier. Across all industrial and laboratory contexts, vacuum generation requires sealed chambers. Atmospheric pressure infiltrates any vacuum immediately upon valve opening, and containment is achieved structurally, not gravitationally. No scientific experiment demonstrates gas pressure maintaining equilibrium within or next to a vacuum without a solid barrier separating. If gravity can supposedly perform this function, demonstration is required. Without demonstration, this claim remains theoretical. If the globe model rejects containment, it must produce a working, macro-scale demonstration showing how gravity can substitute for containment without violating entropy. In contrast, an enclosed Earth cosmology, contained by a firmament, dome, or boundary layer, provides such physical enclosure and is consistent with pressure-retaining systems. Lastly, let's examine optical occlusion, or the fact that we can see too far. On a sphere, optical occlusion occurs because surface convexity blocks straight-line vision, and this forms a geometric horizon. This means objects beyond the curvature limit should be partially or fully hidden depending on distance and elevation. In reality, long-range visibility tests frequently show cities, mountains, platforms, ships, turbines, lighthouses, and other objects visible at distances where curvature math predicts full or significant occlusion. For example, the Chicago city skyline is often visible and photographed from the shore across Lake Michigan 60 miles away. At this distance and elevation, the predicted curvature drop on a globe of given proportions is a full 2,400 feet. The tallest building in Chicago is the Sears or Willis Tower, which tops out at 1,729 feet. This means the globe model requires the entire Chicago city skyline, including the very tallest building, to be fully occluded below the horizon. In reality, we can observe the skyline visible and intact, non-inverted, stable, reproducible, and confirmed via infrared and optical equipment. The mainstream explanation offered for this phenomenon is a superior mirage. However, superior mirages are inverted, highly unstable, temporarily short-lived, and spatially fragmented. Chicago's skyline displays none of these properties. Thus, the globe model relies on various theoretical patches, such as refraction to explain why we see too far, gravity to explain why gas doesn't disperse, and inertia to explain why we feel no motion, whereas a stationary enclosed plane model requires no such patches. The observed demonstrations of water laying flat, pressure requiring containment, and seeing the city show our actual scientific reality, whereas a spinning globe within a vacuum of outer space remains a theoretical, mathematical construct appearing in textbooks but absent in physical, scientific testing.